In this lecture, we're going to be talking about taking the derivative of a vector. Now, this becomes really important as we've defined various frames, and say we know what a vector is within a frame. How do we define that? And we know some relationships about that vector with respect to the frame that it's defined in. How do we define that in terms of a different frame, and how is it evolving in that other frame? And so this is vector differentiation. Well, I want to clarify here that this is not point differentiation. And so if we talk about the difference between a vector and a point, a vector, right, it is a direction and magnitude. And one of the things we've seen in a previous lecture is that the vector is constant under translation. That's an important thing to note. So if it's constant under translation, something that's purely translating, the vector is going to have a time the vector between the frames, differently. A vector defined in frame, like the body frame, for instance, and or a vector defined in the vehicle frame is going to be, if it's constant in the vehicle frame and the vehicle frame is moving, that vector is also going to be constant in the inertial frame because it's just a direction and a magnitude, and there's only translation between the inertial and the vehicle frame. Okay, so let's jump into it. Say we have our body frame, and it really could be any frame, is rotating with respect to our inertial frame, Fi. So, and again, this could be any two different frames. And we have a vector P defined on this line, and it's moving in the body frame. So note that it's not fixed in the body frame. It's actually, we know how it's moving in the body frame. And we want to know what its time derivative is in the inertial frame. So to relate the inertial frame and the body frame, we have this other axis, or this other vector, sorry, not axis. This is going to be our omega b sub I. So let's write that out. Omega b sub I is the vector defining the rotation of f super b with respect to f super I at a particular point in time. Okay, so it's going to have, if we were to define it, say in the body frame, which would be its most natural way to be defined. So say we put this in the body frame, then if we did WBI in the body frame, this would tell us we'd have an X component, a Y component, and a Z component. So how we're instantaneously rotating about each one of the axes. It would be how the instantaneously in fact, that actually might be more natural to define in the inertial frame, right? So how is it rotating? We can define it in either frame, and we can transform it back and forth. You guys are now pros at that. How is it instantaneously rotating about the X, Y, and Z axes? Okay, so we have this vector that's telling us the relationship between frame B and frame I. All right, so let's just start off from the beginning. So we have P, and if you recall, we defined P in terms of an X component, a Y component, and a Z component. And this X component is in terms of, we multiply that by IB, the Y component by JB, and the Z component by KB. So in other words, this would just be equal to, and we should be writing this well, the vector is what it is. In this case, if it were P sub B, then this would just be equal to Px, Py, and Pz. Okay, but we can define the vector as such. And remember, I sub b is just that vector that defines the body frame, and it's not associated necessarily with a frame. So this is just that small bit of notation in the book that I would prefer if it was written I sub b, j sub b, and k sub b. Okay. Excellent. So we have this vector defined. Now, if I had a vector that's fixed in the body frame, so for instance, we have, in this case, we define I sub b. We can actually define, and I meant to mention this as we were talking about omega sub b, b slash I. We can define the time derivative dt, and we're going to put the time derivative with respect to the inertial frame, right? Of I sub b, and I'm going to write super b to match the book notation, if I can. There we go. We can define this as omega b slash I cross I b. Okay, so this we're going to just take as a fact, right? And it's not too crazy hard to prove, but let's just take that as a fact, and we're going to write this as I b, and we'll write it as a dot, and I'm going to put that's the dot notation over an I or a j. It's kind of annoying because they already have a dot. So we'll write our j dot b could then be defined as wb sub I cross jb, and we'll have, in this one it'll be actually easy to see the notation, right? wb I cross kb. And really we could replace I, j, and k with any vector that's constant in that body frame. So we're going to just take that as a fact, and now we'll run with it. Okay, so if we were to look at the time derivative of p, and we're going to define, if we were to, let me take one step back. If I were to define, so let's take this as an aside. If I were to define the time derivative with respect to the body frame of IB, well, that would just be 0, right? Because it's not moving with respect to the body frame. Similarly for the J and the K. So if it's constant in the body frame, then its time derivative is going to be 0, and this would be a 0 of 3 dimensions. Okay, so now we've got these facts, and with this aside, so we can take the time derivative with respect to one frame or the other. So that's how we're using this notation. This is with respect to the body frame. This is with respect to the inertial frame. Excellent. So let's break down this. Let's find what the time derivative with respect to the inertial frame of point P is, right? Now we can just quickly break this out. Each one of these components, it's just two components multiplied together, so we're going to use the chain rule to get the time derivative, right? So we're going to do Px dot times IB. Let's see, did I do that? Yeah. And then we did plus Py dot times JB. And note that I don't have a dot above the I or the J, plus P Z dot KB, plus, now we got to take the time derivative of the second element. So we're going to get plus px ib dot, oops, sorry, didn't really need that, plus, and that this is the big dot to note that it's the time derivative, plus py jb dot plus pz kb dot. Okay, so all we've done is look at the chain rule. Okay, so now if we look at this first row, this is actually just the time derivative with respect to the body frame of P. So in that frame, recall that I, J, and K are constant, right? So this we can relate as just the time derivative of P with respect to the body frame. And now we can then, we can kind of start to simplify things just a little bit. Okay, so we have these relationships that we've already defined, right? So we can now start to plug in these relationships for these components, right? So if we keep writing this down, I'm going to say that this is equal to, and I'm just going to substitute in our relationship. It's d TB of P. So that's that whole red circle. And then we would say that we have Px, and we have we're just going to substitute in our I. So WB/I cross IB plus, then we have PY, and we have our WB/I cross JB plus PZ WB/I cross KB. Again, where this is just I dot, this is J dot, and this is K dot. Okay. Excellent. Well, if we were to look at these terms, we just have a bunch of cross products. If we were to write these all out, we could actually just write these terms out as the cross product between WBI cross the vector P, which is kind of cool, because we have Px times IB, Py times JB, and Pz times KB. So that's just WBI times P. So now, if we look at the final value of this derivative, we'll write it again, ddt of the inertial frame with respect to P is just going to be equal to ddt in the body frame of P with respect to P, plus WB/I cross P. So that's where we have it. So we have this nice relationship, and we're going to use this relationship as we start to define the effective forces and moments on the states of our aircraft.